Hi guys, this is Dr. Marshall, and this is the first lecture in the frames of reference, position, displacement, and distance discussion in the kinematics in one dimension unit. Okay, and if you're watching this video, I'm assuming you got there by first coming to the physics homepage and then going to assignments and then going to this particular participation assignment and clicking on that, and then printing out the worksheet and then clicking on the Nearpod lesson, and then going and starting the video so that you have both the video and the Nearpod lesson going at the same time, and that you are able to easily switch between these by clicking on their little icons or their tabs in the toolbar above the video assignment or the video screen. And so you can see here that we've moved to the welcome page to the Nearpod, and we're just going to walk through this. You need to follow the Nearpod. You can have the lecture open and just follow the Nearpod by clicking back and forth. First thing we're going to do is just put your name in there and then join the lesson. And the first thing I have is an open-ended question. So just to get your brain thinking in physics mode, write out the core statement of our physics graphic organizer. Blank gives rise to blank, which gives rise to blank. Okay, you know what this is? Okay, so type that in, and the Nearpod will take care of registering the fact that you did that. I'm just going to write Marshall was here because I don't want to deal with the issue right now of giving you the potential answer here. Okay, so once you're done with that, go ahead and go on. I can go on, and you can just stop the video if you need to have more time for input. So what we'll always see at the beginning of our discussions is that a portion of the course graphic organizer will appear at the beginning of the set of notes, highlighting the individual concepts to be talked about. The intent is to be able to visualize where the individual concepts fit into the big picture study of physics. For this particular discussion, our learning target will be you will be able to list and give examples of 3 different ways of describing motion. And the reason that we're going to do this is because the motion or the description of motion is most complete and understandable when it is not only described qualitatively with words, but also quantitatively with mathematical formulas and data, and visually with graphical representations. Hang on. Okay, so learning target. First learning target. The student will be able to list and give examples of 3 different ways of describing motion. And the reason that we want to do this is that the description of motion is most complete and understandable when it's not only described qualitatively with words, but also quantitatively with mathematical formulas and data, and visually with graphical representations. And the way that we're going to check on this is if I give you qualitative or quantitative or graphical information about a motion, you will be able to provide corresponding information for the other 2 ways of describing that motion. So let's go ahead and go to the next slide. So consider a quantity of matter, any quantity of matter, and I'm going to use this term enough that we'll just call it a quam. And if this quantity of matter is in motion, the motion can be described in a variety of ways. Remember that I'm going to use the notes feature of Nearpod here. Remember, again, you can take your own notes here if you want, and then have them sent to your email, or you can have them sent to Google Drive or OneDrive if you wanted to. But I'm just going to use this to type out the answers that we want for the particular blanks that you're filling in so that you can see what goes in the blanks. So the first way that we're going to describe motion is by just simply using words or through language. Okay. The second way that we're going to describe motion is mathematically, through the use of mathematical formulas or mathematical words. And then the third way that we're going to describe motion is graphically. And I'm going to explain what we mean by all three of these things here now. Okay, so those are the three things that go in the blanks here on your worksheet. Let's go to the next slide, and I've got a question for you. It says, think about the motion of things around you in the world. Consider the motion of any object you choose and write a description of that motion below, giving an indication of the type of motion, whether it's constant or changing velocity, an indication of the magnitude or the value of the velocity in descriptive terms, for example, slow or fast, or really fast, and then the direction of the motion. And so for the answer on the worksheet, you can use your answer here or the one that I give in the notes. And actually, I didn't give one in the notes, so I'll write one right here. Okay, so I'm going to say the red sports car accelerated from rest to a high velocity in a short period of time in an east direction. Okay, not the best sentence in the world, but it covers the idea that the motion of this vehicle is changing and that it's going to have a high velocity and it's going east. So you can use that sentence.
Teachers and staff, for those of you that are involved with the ACT tomorrow, there is a meeting up in room 206. That's Ms. Nichols' room, and we will be starting that at 12:30. Thank you.
Okay, here's the announcement in the background. So you can either use that statement or you can create your own. So I'm going to submit that because I need to in order to move on, and you can go to the next slide. So even though we aren't using numbers, when describing motion using language, we will try to use modifiers that at least give a general indication of the type of motion, how fast the motion is, and the direction in which it is moving. Okay, so try to use those features. Let's go on to the next slide. Give an example of describing motion using a mathematical expression. Okay, so we're just going to type out a simple formula here for this particular thing, and we're going to say x, which is my position, is going to equal velocity times time. So it's a very straightforward definition or a way to find how far something went given the velocity and the time of the motion. So we can get a good idea of just how fast something is moving using language, but this is only a qualitative statement of the motion. It doesn't have a number associated with it, and so we can actually quantify or put actual numbers to various rates of motion using mathematical formulas. Now we'll focus a great deal on learning and using mathematical rules that describe motion, but we'll also spend a lot of time making sure we can communicate these mathematical concepts using our words. So go to the next slide. So the third way we're going to look at describing motion is through graphical representations. Okay, and this graph that you see here and that's on your worksheet is called a position-time graph. And you can see that time is on the x-axis and position's on the y-axis. And this is going to confuse us a great deal. So I want to go through this just a little bit to illustrate how this might work, just so we can start with a little bit of a less confusing representation as far as graphics goes. But go ahead and go to the next slide and I'll show you what I mean. So type of graph shown is a position time graph because the graph shows the relationship of the position to time by plotting the position to time by plotting position on the x-axis, y-axis, and time on the x-axis. I'll need to go back and modify that sentence a little bit. We'll become very familiar with these in the type of information they can visually demonstrate to us, but initially they'll make us very uncomfortable. We're used to thinking of motion in one direction as occurring in a straight line in a left or right to left direction. But motion on these diagrams is shown as position compared to an origin on the vertical axis. The farther away I am from my origin, the more vertical distance I have. Okay, so let's see how this works. So we start by showing the position at time 0. In this case, we'll say that the position at time 0 before motion has started is 10 units to the positive side of the origin. So I'm starting 10 units away from the origin. That's my start position, and it doesn't really matter if I have that on a vertical axis or a horizontal axis, except that we're used to dealing with this kind of information on a horizontal axis, but now we're going to get used to it on a vertical axis. So what we're going to say is that notice that our brain would tell us this means 10 units to the positive side of the origin on a horizontal frame of reference. And you can see that if I put this on a motion diagram, or something we're going to call a motion diagram or frame of reference, I can visualize that my starting position is in fact 10 meters from the origin. So if this is my origin, then here's my starting position. Okay, but again, notice that in this case on the position time graph, it's on the vertical axis instead of the horizontal axis. So let's go ahead and go to the next slide. Now let's say over the next second, after a total of 2 seconds, the object has moved to a position of 30 units on the positive side of the origin, and that's indicated here at 2 seconds. My position is at 30 meters to the positive side of the origin. Unfortunately, the graph now gives us the visual impression that the object is actually traveling at an angle, but this is not the path that the object is taking, right? This is not a graph of where the object is going. It's a graph that's showing us where we're at a certain amount of time, but it's not the actual path that the object is following. If I want to see a representation of that, I can look over here at this graph or at this diagram and see that I went in my first 2 seconds from a position of 10 meters to a position of 30 meters. Okay? So actually this should say x sub 1 instead of x sub 0, because that's where I was also after my first second, was this 10 meters. Okay, now I'm going to have to switch videos here because I'm running out of time on this one. I only get 15 minutes of video and we're pushing that right now. So stop this video and go to the next one. Okay.